Welcome to this video, which is about how you can examine density with young children. Density is something that most children have lots of experience of. Even a very small child will put food in their cup just to see what floats. And most children, given a chance, will throw rocks and sticks into a pond. What I want to do with this video is to give you a few examples of how you can expand the understanding of the concept of density. So what is density? Well, the easy answer is that it's a mass divided by volume. But that's perhaps not so easy for a preschooler. Many young children perceive heavy as the same thing as large. We can challenge the children by comparing weights and volumes of different materials. In this first example, we pose the classic questions: what is heavier, a kilogram of lead or a kilogram of cotton? This is probably obvious to most of you, but at this point, there are always a few of my university students who look a bit confused. So just to make sure everyone's still on board, the mass is the same, it's only the volume that's different. Some of you might react to the fact that density of cotton is not really what you see in the picture, as it's filled with air. If you compress it, the density will be higher. Even so, the density is still less than lead. Another way of illustrating density is by comparing items of very different weight, but similar volume and shape. I here have a marble and a rubber ball. Very similar in shape, but very different in weight. Now, ideally, I should have the same color as well, because very young children can sometimes get confused and think that color influences the object's ability to float. Now, this is a good idea in general, to only compare one thing at a time so that the children don't get confused as to what actually influences the object's ability to float or sink. Many activities connected to density in young children are spontaneous. Let the children examine freely, but challenge their understanding by using productive questions and by supplying more challenging materials. In this picture, the children were examining the floating ability of food and toys. They also used leather magnets from the fridge. The magnets stayed afloat until they were filled with water, and then they sank. But what happens if we remove the small magnet from the plastic letter? Can you still make it sink by filling it with water? By using productive questions, you can focus their attention and you can let them form hypotheses that can be tested or revised. What do you think will happen if? In this example, the children learned that shape can also influence the ability to float. When you introduce shape to the concept, what makes an item float, you can make boats from different materials. Even boats that are made from materials that float can teach children about construction, since they capsize if they are too light. How do you construct a boat in order to avoid it capsizing? It's more challenging to make a boat out of a material that has a higher density than water, like metal. This sounds tricky, perhaps, but it's not actually that hard, and you don't have to make it very difficult. You can make a boat-like structure using a lid or a can. You can also use a can, but you'll probably find that unless you put some weight in the bottom of the can, it will tip over and it will capsize, just like the boat made of bark. And that's why you have ballast in the bottom of ships, to make them sink down further in the water to be more stable. Why do boats made of metal float? Metal has a higher density than water, but a boat is not only made of metal, but also cargo, furniture, and perhaps most importantly, air. In order to avoid tipping, you also need something heavy in the hull, sometimes called ballast. The combined density is less than water. The force that pushes the boat into the water must equal that of the upward force, and that includes the weight above water. If the downward force is greater, then the boat will fill up with water and sink as water replaces air in the hull. Use the children's own experience of floating devices. Perhaps they have experience of life jackets in a boat, or back bubbles or floaties in a pool. Talk to the children about what the properties are of these floating devices. Often they contain air, for example, or they contain pockets of air, or are simply made of very low density materials. To illustrate how floating devices work, you can use an orange in a glass of water. If the orange has a thick peel, it will float, but if you remove the peel, it sinks. Another life jacket illustration is the raisin elevator trick. You place raisins in a glass of well-carbonated water. The raisins will initially sink, but then the rough surface will generate small bubbles that will eventually lift the raisins up to the surface. When they break the surface, they will lose the bubbles and sink again. So far, we've looked at the densities of solid objects in relation to water. But different types of liquids can also have different densities. Oil, for example, and other forms of liquid fat will have a lower density than water, which is why they end up floating on top of the stew. As you can see in the picture, if you place a bit of plastic, it will usually float in water, but it will usually also sink in oil. Depends on the type of plastic, but most of the time that's the case, which means that it will end up in the layer in between oil and water. Water has different densities depending on temperature. Ice has a lower density than water, which is why it floats. This is counterintuitive, as most substances have highest density in solid form. However, when water freezes, the molecules form a pattern where there is space in between the molecules, as you can see in the picture. That is because of the shape of the water molecule. The two hydrogen atoms are on average positively charged and are at an angle with the oxygen atom, which has a negative charge. In other words, the water molecule has polar properties. When water is in liquid form, it also has different densities depending on temperature. The highest density is around 4 degrees centigrade. But for the activities with children, we can just simplify and say that cold water has higher density than warm water. As you can see in the picture, I've used blue water to illustrate cold and red to illustrate warm water. I've placed cold water in a small glass that I covered up with cling film. When it leaves the glass, it ends up at the bottom. When I did the same with hot water, it moves to the top of the jar. I've chosen a logical color symbolism, as most children are already familiar with color codes connected to temperature. Imagine if I'd used yellow and green, then the effects would have been the same, but the children would not necessarily remember which color was warm and cold, and they might therefore also be confused as to whether hot or cold water has a higher density. When water contains salt, it also has a higher density than fresh water. In this experiment, we placed dyed ice cubes in water to see what happens when it melts. And in one glass, it was fresh water, and in another, it was salty water. And in the fresh water, when the ice melted, the blue dye, in other words, the cold water, went to the bottom of the glass, whereas in salt water, it stayed on top. And this is because salt water has a higher density than cold fresh water. You can illustrate this by putting a potato in fresh water and then adding salt. Initially, it will sink to the bottom, but as more and more salt is added, it will start to get suspended in the water column and eventually float to the surface. Now, you need quite a bit of salt for this to actually work. So I suggest you start with a deciliter of salt rather than a teaspoon, unless you want the children to give up. Gases also have different densities. The air contains a mixture of gases, including primarily nitrogen and oxygen. Helium is another gas that has a lower density than air. That's why if you have a balloon, a helium balloon, and you let go of the string, it will fly off. Air can also be of different densities depending on temperature. Hot air has a lower density and will therefore rise, move upwards in the atmosphere. That's why it's the hottest at the top bunk of a sauna. It's also how a hot air balloon can work. In a hot air balloon, you have a burner underneath the balloon, and when you use the burner, it will heat up the air in the balloon and the balloon will rise. When you turn off the burner, the air will cool down gradually and you will move towards the ground. Now, when the density changes because of temperature, is it the mass or the volume that changes? This might not be obvious to young children, and to illustrate that it's a volume that changes with temperature, you can place a bottle in the freezer, and when you take it out and the air inside the bottle is cold, you place a balloon on top of the bottle, and then you place the bottle underneath hot water tap, and the expanding air will fill up the balloon, at least partially. When this experiment was done, we placed the lid on top of the bottle again, and we put the bottle back into the freezer, just to see what happens to the air inside the bottle as it gets cold again. The topic of density, or perhaps more accurately, what items float or sink, can be expanded either by the children's own discoveries or because you want to challenge their understanding in some ways. In this picture, the child is examining water striders that are running across the surface. This is not because of density, but because of water surface tension. Water surface tension is a result of the strong bonds between water molecules. It's like the molecules are holding on to each other, like they're holding hands. That is because of the polar properties of water molecules that I mentioned earlier. This is why you get drops on a leaf, and it's also why you can add so much water onto a coin without it spilling over. Washing up liquid removes the surface tension. That's because it's made up of long molecules where one side is polar and the other side is non-polar. And the polar side of the molecule mixes easily with water and breaks up the strong molecular bonds between water molecules. You can get a thin metal wire to float if you shape it into a flat object. This is a bit tricky, and you might have to try again. And when you do that, make sure you actually dry the wire, because it won't work with wet objects. When you finally get your metal to float, you can pour washing up liquid and actually watch the surface tension disappear. Make sure that the children actually understand the difference between surface tension and density. If we were to pour tons of detergent into a lake, which I don't recommend, by the way, would the boats on the lake sink? The densities are not affected by changes in surface tension. Only very small and light things can be held up by surface tension. If you thought this video was useful or interesting, please like and subscribe for similar videos.